Can you guys hear me?
Yeah, I can, though it's really echoey.
You can hear me?
Can you hear me?
Yeah.
I can hear you. It's just your mic was somewhat echoey before. I'm not sure if it'll keep going, but
Yeah, there seems to be some feedback, right?
yeah.
Let me see. Can you hear me now?
Yeah, I can.
And there's no feedback, right?
Not that I can tell now.
Okay. And you can see the screen, right?
Yeah, I can.
Okay. Good morning. What I want to do today is very quickly wrap up chapter 1, the discussion of crystals and lattices, and then jump into chapter 2, which is basics of modern physics, quantum physics. And then next week, we'll move into quantum mechanics. And after that, things will get a lot easier because we'll get into semiconductors and semiconductor devices. Last time, what we said was you have to define a crystal in terms of a mathematical abstraction called a lattice, which is an infinite periodic arrangement of points in space, where the symmetry determines the type of lattice, not the actual dimensions between the lattice points. So for example, on the right-hand side over here, in the lower half, I'm showing a square lattice because these points are arranged in a square. On the other hand, in the other half, I'm showing a rectangular lattice in the top half because you can see clearly this fundamental unit block, the primitive cell, is a rectangle. And although a square is a special case of a rectangle, since a square has additional symmetry where these two vectors, which are called the primitive vectors A and B, are equal to each other, while in the rectangle they are not, you call a square a different type of lattice because these additional symmetries we'll see have implications for the electronic and optical properties of the semiconductor. Then at these lattice points, so far it's just a mathematical array of points where the symmetry determines the lattice type, okay? So in the case of a square, for example, what type of symmetries am I talking about? Well, clearly, if you rotate the lattice by 90 degrees, you go back to the original lattice, 180, 270, 360. So those are examples of rotational symmetry. Or you could take a plane like so and use that as a mirror to reflect the left-hand side onto the right-hand side and vice versa. So that's an example of reflection symmetry, and so on and so forth. And all of these, although we won't get deeply into those, if you take a graduate course, you'll see have very, very important implications for semiconductor devices. Now, then at these lattice points, you have to put in a physical entity, which is called a basis, and that's shown on the right, on the left-hand side, where the basis happens to be, say, a single atom, these blue atoms. But in general, the basis could be more complex. Okay, so it could be a group of atoms that have to be put at every single lattice point in the same orientation. Otherwise, those correspond to defects. Then we saw how to do calculations based on these lattices. And we said that you always figure things out on the basis of the primitive cell, which is the most fundamental building block. Or sometimes if the primitive cell has a very odd geometric object, you're better off choosing a larger entity, the unit cell, which is hopefully more regular. So in this case, the primitive cell itself is a square. So, there's no need to go to a larger entity, but in some cases you might have to. And the principle is very simple. So you always work in terms of, let's say, the unit cell, okay, which in this case is this square. So how many atoms belong to this unit cell? So if I focus on, say, this particular unit cell, I see that I have 4 lattice points at the corners, but only 1/4 of each of those points should be counted towards this square, right? Because, say, this lattice point is shared amongst 4 neighboring squares. Okay, so 1/4 times 1/4 means I have only 1 lattice point. And then if the basis happens to be 1 atom, as shown over here, multiply that by 1, so I only have 1 atom per unit cell. Okay, so if the side of the square is A, the area of the unit cell, this is of course a two-dimensional crystal, so the area of the square is A square. So the density, for example, would be 1 divided by A square. Okay, so be prepared to do calculations like this for 2D or 3D lattices of different types. Now, before I leave this topic, I just wanted to very briefly mention that in nature, crystals are in general never going to be perfect. You'll have all kinds of defects in the crystal, some of which can have very bad consequences for semiconductor devices. Some are avoidable, some are not, okay? And you can categorize defects in terms of the spatial dimensionality of the defect. So for example, the simplest ones are 0-dimensional or point defects. And the simplest example of that is a missing atom, as shown over here, which is called a vacancy. Okay. And it turns out at a finite temperature, you'll always have a finite number of these vacancy type defects. Okay. So we won't go into the mathematics of that, but from basic thermodynamics, one can prove that you can never have a totally perfect crystal with zero defects at finite temperature, because the atoms are jiggling around because of the thermal energy. A few of them will pop out of their lattice locations, and you'll have a finite number of these vacancies. Another type of point defect that's very common is interstitial, which is an extra atom which doesn't lie on the Bravais lattice sites, but instead lies in an interstice or a void between the lattice points. Okay, so this is also very, very common. And very often these vacancies and interstitials occur in pairs, because if a silicon atom over here popped out of the lattice location to a neighboring site, clearly you get a vacancy interstitial pair. Those are called Frankel type defects. Okay, you can also have defects due to impurities. So for example, if I replace one of these, say, silicon atoms with a red atom, maybe a phosphorus impurity, okay, that would be an example of a defect, because the location is the same as that of the silicon atom, say, but the red atom clearly, in the case of phosphorus, is a different type of atom. So that's an example of a defect or an impurity. All right. Now, as I pointed out in our introductory lecture, you would sometimes put in phosphorus impurity type defects on purpose, because they then act as these donor type states, where the fifth electron in the valence shell of phosphorus is given off to the lattice and gives rise to conduction electrons. Conversely, if we had a column 3 impurity on the substitutional sites, those would be acceptor type impurities. Now, mind you, the impurities, the donors or acceptors, have to lie on the lattice locations. If the impurity lies in a void, it wouldn't act as a donor or acceptor, because clearly then the bonding of the electrons is all messed up, right? So donor or acceptor type impurities have to be on substitutional locations. Now, I also want to point out that when you hear the term impurity defect or defect, you get a knee-jerk reaction that, gosh, defects are definitely bad, right? Now, many defects are, right? But in the case of impurities, which are the donors or acceptors, those are intentionally engineered defects to change the electrical conductivity of the semiconductor. So, sometimes defects are purposely put in to get the functionality that you want. So these are examples of zero-dimensional or point defects, and they're very, very common. The next would be one-dimensional line defects, and an example is shown over here. So what I'm showing is, on the right-hand side, you have a certain number of lattice planes, but then on the left-hand side, you can see clearly, if you count the number of planes, you have fewer ones. And as a result, this particular plane doesn't go all the way to the left-hand side. It terminates over here. Now, if this was a three-dimensional object, looking into the plane of the board, it would be a line, right? This thing is a plane, but then it terminates in a line perpendicular to the plane of the board. So that would be a one-dimensional line defect, and that's called a dislocation. Another example of a dislocation is shown in this figure over here, where this plane of atoms doesn't go all the way through, and that would be a line if I look at it in the direction perpendicular plane of the board. Now, these, in principle, can be avoided, but in some cases, you end up getting them, all right? So why might you get them? So that's shown in the right-hand side as a typical example. So we'll see that in many cases, you'll be working with not a simple semiconductor, but stacks of semiconductors. So you could start, for example, with a silicon substrate, which we saw in the previous class as a cubic FCC lattice, a face-centered cubic lattice, with a lattice constant of 5.43 angstroms. We did that calculation last time. Now, on top of that, you may want to grow a single crystal layer of germanium or some alloy of silicon germanium, maybe 60% silicon, 40% germanium. Let's not worry about how you grow them. You can grow them using the techniques of epitaxy or molecular beam epitaxy that we just very briefly mentioned in the last class. Now, the point to note is germanium has a lattice constant, which is about 4% larger than that of silicon. If it's silicon germanium alloy, the lattice constant will depend on how much germanium I put into the alloy. So as a result, when I start growing a silicon germanium alloy on top of the silicon, what would tend to happen is these larger squares would get squashed in this direction so that the planes line up as shown over here. And if you take a square or a cube and you squash it in the XY plane, it would get elongated in the Z direction. I'm calling this the Z direction. And these are the XY directions, okay? So I take the cube or the square, squash it in the XY plane, gets elongated in the Z direction. And that's why you end up getting a rectangular lattice in this cartoon view on the left-hand side, okay? Now that then introduces mechanical strain in the layer of silicon germanium, because then I have to squash it to fit the planes with respect to the underlying silicon planes. And it works for a while, but then if the layer thickness is very, very large, at some point the strain energy becomes so large that it can give rise to defects as shown on the right-hand side over here. Okay, these are sometimes called misfit dislocations because these dislocations are created by the mismatch or the misfit of the lattice constants of what I'm trying to grow on top of the substrate. Once again, these are very, very interesting material systems that we'll get to talk about, once you get into devices. And I can guarantee you, you have layers like this in your cell phone. So you have things like silicon germanium strain systems on top of silicon, which are used for making very high frequency transistors, RF signal processing type transistors that you have in your cell phone. So this is not just an exotic physics, there's real practical ramifications. And we'll discuss the fun things when you talk about MOSFETs and things like that. Moving on, you can also have two-dimensional defects. And one example of a two-dimensional defect that is unavoidable is the surface of a crystal. As we discussed last time, a mathematical definition of a crystal starts with an infinite periodic arrangement of points in the lattice, right? And of course, we said that no real practical crystal could be infinite in extent. Not even Intel or TSMC could afford an infinite size silicon crystal, okay? So all silicon wafers have a finite extent, and therefore the surface of the crystal is one massive defect. And those have dangling silicon bonds because, remember each silicon has to have 4 covalent bonds. So in the case of surface silicon atoms, you see that 3 of the bonds are satisfied, but the 4th one has no atom to stick to. So these are called dangling bonds, and those then give rise to defects called surface states. Turns out to be extremely important for making functional semiconductor devices. It took engineers and physicists a long time to recognize the importance of that. Prior to recognition of that fact, when they tried to make transistors on a bare silicon surface, nothing would work. But then they figured out you can satisfy some of these dangling bonds by growing a layer of silicon dioxide where these oxygen atoms tie up these dangling bonds, and you reduce the surface state density, and only then could you make things like MOSFETs. Then finally, you have three-dimensional defects, and an example is shown over here, where maybe I'm putting in phosphorus atoms on substitutional sites, but if I try to jam in very many phosphorus atoms and exceed what is known as the solid solubility limit, which is the maximum amount of phosphorus that I can dissolve in the silicon crystal, you can form a three-dimensional macroscopic defect such as this, okay? Now, the solid solubility limit analogy would be, if you take a glass of water and you add a little bit of sugar to it, the sugar will all dissolve, right? And you keep adding sugar, and at some point, you saturate the water with sugar, and you can't dissolve anymore, and then the sugar crystals would form a pile at the bottom. So it's sort of the analog of that in the solid phase. One final comment before I leave chapter 1, and this is meant to be a preview of what we'll be discussing in chapters 2 and 3 and so on and so forth, okay? So don't worry about the details. I just want to get one concept across, okay? So what I'm trying to show over here is the fact that when you look at a crystal, because these atoms are a periodic arrangement in space, you can use the concept of Fourier series or Fourier transforms, right? Because you study in your 302 or I'm sure in 411 and many other classes that, for example, if you have a time-dependent signal, f of t, which is say a sine wave, which is a periodic signal, very often instead of defining in the time domain, you're very often better off defining it in the frequency domain by taking the Fourier transform of this as a function of frequency omega, and then this nice time-dependent signal, a sine wave, is a single frequency component, right? Or, if instead of a simple sine wave, maybe it was a more complicated function, but still periodic, right? So maybe it has wiggles like this, but it's periodic, okay? So then you may have a couple of different frequencies, maybe omega 1, omega 2, and so on and so forth, okay? So the point in Fourier transforms is if you have something that's periodic in time, you can also define that by taking the Fourier transform in frequency space, f or omega or whatever, okay? Now, I don't know if you've taken a course in digital signal processing. There, you may have learned that you can take an analog signal and you can take samples at different time locations. Okay, so now this time-dependent signal f of t is sampled. So if it was a sine wave, I may get something like this. I'm not doing it very well, maybe, but imagine I have an envelope is a sine wave, but it's not a continuous signal. I take samples at different locations at a sampling period of delta t, say, okay? So here also, you can now take the frequency, the Fourier transform of a sampled signal in the time domain, which is periodic, okay? And you get frequency components. But now you have an additional twist, and that is the highest possible frequency that you can get is related to the sampling rate, delta t, okay? And that's sometimes known as a Nyquist frequency. Some of you may not have taken a course in digital signal processing, so these things may not make too much sense. Don't worry too much about it. The real important thing to remember is if I have something that's periodic in time, in the frequency domain, I can take the Fourier transform and I get these frequency components. Well, in a crystal, I have something that is not periodic in time, but it's periodic in space, okay? So once again, you can take a Fourier transform of something which is a function, periodic function in time, where f of x plus a equals f of x, where a is the lattice constant, right? So if I now take the Fourier transform, okay, so now I can define things in Fourier space, the analog of frequency, and the Fourier space is known as wave vector space, k space, okay? So when you hear the term wave vector k, that's what I'm talking about, okay? And we'll look at functions of the type, say f of x and t, so time-dependent waves propagating in the signal, propagating in this periodic crystal, which will be of the form e to the power I kx minus omega t. Okay, so x and t are, of course, the spatial and time domain terms, and k is sort of the the Fourier transform conjugate in the space domain, and omega the Fourier transform conjugate term in the time domain. All right. So an example of such a wave propagating in a crystal is shown in a cartoon view over here, where these red points might be the atoms, which are initially at the lattice locations, okay? But then I can imagine a elastic wave or a sound wave propagating in the crystal, okay? And we'll see this in chapter 3, where you can imagine, pulling these atoms from the equilibrium location. But then as soon as I let them go, they'll oscillate back and forth because these atoms are connected by imaginary springs, okay? Now, of course, you don't really have springs in there. The springs are just model for the interatomic forces that you have in a crystal that we'll discuss later on, okay? So these waves will propagate, okay? Now, the thing to note is, if I'm looking at elastic waves, I really am only interested in the locations of the waves at the lattice points, right, which are these red dots. And that can be described in this particular displacement scenario as a wave where this is half the wavelength, right? But you could also say, now I want to describe that as a shorter wavelength, which is this wave over here, right? Now, I don't really have any atoms at these locations over here, right? So this shorter wavelength description and this longer wavelength description are identical because I have a medium that is discrete. And that goes back to this discrete sampled signal, the analog that you talked about in the case of digital signal processing, okay? So once again, in chapter 3, when we start getting into this into more detail, we'll see that just like you have a maximum possible frequency, the so-called Nyquist frequency for a digital signal. Similarly, in K space, which is the Fourier transform space of position, you have a maximum K vector, which is known as the Brillouin zone. So just keep this at the back of your mind. And so when I throw these terms out, you have a rough idea of what you're talking about, okay? So essentially, in chapters 2 and 3, we look at various types of waves propagating in a discrete medium, which is the periodicity of the lattice. Now, the types of waves could be different types of waves. So I've just talked about this last elastic waves or vibrational patterns of the atom. But in many cases, we'll be looking at electrons, which propagate in the crystal. But the electrons we'll see from quantum mechanics also have a wave character that's known as the de Broglie wave. That's the subject of the next chapter, okay? Now, one final thing before I leave this, and this is all meant to be a preview, is it turns out when we do our mathematical description of wave propagation in a crystal, we'll end up having 2 levels of periodicity. The first level of periodicity is due to the periodicity of the crystal itself, where I have a lattice constant of A. So A is your lattice constant between neighboring atoms, okay? But then on top of that, we'll play a mathematical trick where we'll take a crystal of finite dimensions like this, and we'll try to figure out what the wave propagation looks like, okay? And if I had a finite crystal where say this elastic band was tied up at these 2 ends, and I, displace the elastic band, it'll oscillate back and forth and give rise to standing waves. It turns out standing waves are a little bit harder to deal with mathematically than traveling waves of this form, okay? So how do I get traveling waves mathematically? So what I do is I take this finite crystal and artificially map it like so in all space, okay? So if the length of the crystal was L, I take the same crystal, map it by L, 2L, and so on and so forth, so that now it becomes essentially an infinite crystal mathematically, in which I can have traveling waves propagating, and it makes the mathematics simpler. And that mathematical trick is known as a periodic boundary condition, okay? So you take a real finite size crystal, but by mathematically mapping it from minus infinity to plus infinity, you make it look like an infinite crystal so that you can have, traveling waves rather than this standing waves in the system. Don't worry too much about, the details. Like I said, the details will come in chapter 3 when you look at things like band structure. Any questions on chapter 1? So at the end of each chapter in the textbook, we've put in some summary that might be helpful.
So the problems are in the syllabus, or?
Yeah, the problems are in the syllabus, yeah. And they're from the US edition, 7th edition, the US version of the textbook. Okay. And they're due on the dates shown in the syllabus. But, sometimes because of other classes, if you can't make it on the exact deadline, it's okay to, turn it in a couple of days later. I mean, don't make a habit out of it, please. And you have to scan them and upload them on Canvas. All right, so let's jump into chapter 2, quantum physics, modern physics, the second half of which will be quantum mechanics. So in some sense, as I told you already, conceptually, this is perhaps one of the toughest parts of the class. And many students, feel lost, and then they kind of give up and, don't show up for class, or in this semester, I guess, don't sign in. Please don't do that, because once you get over this tough hump, not so much today's lecture, but the next lecture on quantum mechanics is going to be a little bit harder from a conceptual point of view. If you can somehow get over that hump, it gets a lot easier. And number 2, although I will discuss some basics of quantum mechanics, it's just to really set the stage for understanding semiconductors. I'm not going to test you in great detail on deep levels of quantum mechanics. So as long as you get the general idea that everything in nature has a nice unified view, where everything in nature has both a particle type character as well as a wave type character. This is this famous wave particle duality that I'm sure you saw in AP physics or undergrad physics. That's really the basic thing that's important, because when electrons propagate in a semiconductor crystal, they also have this wave type characteristics that's absolutely essential to understand. All right, so quantum physics. It's a very interesting story that basically started at the turn of the 20th century. So a little bit of historical background using light to tell my story, okay? So ever since the days of Isaac Newton and his contemporary Christian Huygens, and then, following that, many other scientists, they had a lot of debates about the true nature of light. People like Newton felt that light consisted of particles. He called them corpuscles, while Huygens felt that no, light is like a wave, okay? And for example, if you look at some phenomena, such as reflection of light, so this is a mirror, say, okay? And I bounce light, we know that the angle of incidence equals angle of reflection. Well, Newton said that, oh, it makes sense, because then you can think of these as ping pong balls that strike the surface and they come off at the same angle. Huygens said, no, you should really think of it as a wave, and the wave reflects, making the angle of incidence equal to the angle of reflection, and so on and so forth, okay? But then there was an experiment which seemed to settle the debate in favor of Huygens, the wave picture. And that is this famous double slit experiment made by a guy called Young. What he did was he took a light source and he shines the light where I'm showing these wave fronts of the light coming out from this light source S onto a screen which has two slits, S1 and S2 cut in the slit. And then on the right-hand side, you have a screen, and Young tried to observe the intensity patterns of the light on that screen, okay? And what he found out was, if the slits were narrow enough and close enough, you do not see single spots of light on the screen. So if light was indeed like particles, as Newton thought, what I would expect, what Young expected was, you draw a straight line and you'd see a spot of light over there, and you draw another straight line and you should see a spot of light over there, and everything else should be dark, right? Instead, what was seen was bright patches of light on the screen. So here's the screen, I'm looking at it this way, right? And that's what you see experimentally. So you see bright patches, dark patches, and so on and so forth. And these are known as interference phenomena or diffraction phenomena, okay? And the way to understand that is, you have to think of these as wave fronts of light, and these waves can, at some points, interfere constructively, and that's shown on this figure over here. So you have a wave front propagating through this slit, and a wave front propagating through this slit, because the waves are spreading out. And at these points, the wave amplitudes add up. That's called constructive interference, and that's when you get a bright light. On the other hand, on certain locations, because of the distance from this slit to that point, so suppose I'm looking at this point. If I look at this slit to this point and this slit to that point, the waves are out of phase and you get destructive interference, okay? So this seemed to settle the debate in favor of the wave picture, because, obviously you can't have such interference phenomena or diffraction phenomena in the case of particles. And then, of course, in the 19th century, Maxwell came up with his theories, and those also seem to bolster the wave picture of light, okay, of light, which is electromagnetic radiation. But the story got interesting at the beginning of the 20th century. But before I get to that story, a few terminologies. So for waves, of course, we know that we have the concept of a wavelength, say lambda 1, which is a long wavelength, lambda 2, shorter, lambda 3, even shorter. So if these are electromagnetic waves, it turns out red waves have a longer wavelength than blue waves, and so on and so forth. So wavelength is the description of the periodicity of the wavefront from, say, one peak to one peak, or one trough to one trough, and so on and so forth. The second concept is frequency. So if you think of something oscillating, so going back to the earlier picture that I talked about, okay, suppose this was elastic band that I pluck and I let it vibrate back and forth. The number of times it goes back and forth, which is cycles per second or hertz, is your frequency, nu. Then you have the amplitude, which is how much the wave bounces up and down, because that's the amplitude of the wave. And it turns out the square of the amplitude gives you essentially the energy contained by the wave. That's called the intensity. So for example, if I have a water wave, which is 1 foot high, the trough and the peak are say 1 foot from one to the other, versus another water wave, which is 2 feet, right? From the trough to the peak, the 2 feet wave wouldn't be twice as powerful, it would be 4 times as powerful, okay? Keep this at the back of your mind. And then finally, you have the concept called the phase. The phase tells you where in the time domain or the spatial domain these waves peak or go to the trough. So for example, I can simply take this red wave and I shift it a little bit. It's hard to draw on the screen. So basically when I'm taking this wave and I'm shifting it, say, a little bit to the right-hand side. So now this trough doesn't line up with this trough. So that gives you what's called the phase difference, okay? And of course, those phase differences are critical to understanding these interference effects, right? So between this wave and that wave, there's a 180-degree phase difference. And that's why you go from constructive to destructive interference, all right? All right, so like I said, at the beginning of the 20th century, people thought, the issue's been sorted out. Newton lost, Huygens won. Light consists of waves, all right? But then, like I said, a bunch of experiments are done, which threw everything into disarray. And the first of those is the so-called black body radiation experiment. Now, there's a whole bunch of experiments. I'm not going to go into them into detail. Just want to get across the concept that light also, under certain circumstances, seems to have a particle type character. So the first such experiment is a so-called black body radiation experiment, okay, where people took a cavity and you have a tiny hole in it, and you look at the you heat up the cavity, and you look at the radiation coming out of it. You put it through a prism so that it splits up into different wavelengths or colors, okay? And then you look at each of these wavelengths, how much intensity that I have. Intensity, remember, is amplitude square, and you plot the intensity as a function of the wavelength of the radiation that comes off, that I can then, map out by using some sort of a prism or whatever, okay? And what was found out was something very strange. People saw the experimental data given by this red curve, okay? Now it turns out, and I'm not going to go into the detailed mathematics, if you stuck to classical wave theory, what you should really have gotten is this blue curve, okay, the so-called Rayleigh-Jeans law, which shows that as the wavelength goes through shorter and shorter wavelengths towards ultraviolet or X-ray or whatever, the intensity should keep going up. And this is sometimes known as the ultraviolet catastrophe, okay? So Mr. Planck at this point came in and said, I can explain this experimental red curve if I postulate that when the radiation, the electromagnetic radiation comes off, although we think of it as a wave, but you should really think of it as a wave which can only come off in packets, where each packet of energy, which was later called the photon by Mr. Einstein, has an energy proportional to the frequency of the radiation, nu, times proportionality constant, which is known as a Planck constant, okay? And what you can have is different integer numbers of these photons that can come out. So if it's a very bright intensity, you have many photons. If it's a low intensity, say over here, I have fewer photons, and so forth, okay? So the intensity I, which in the classical picture varied continuously with amplitude as a square, in the quantum picture of Mr. Planck, said, no, you can't vary the intensity continuously by changing the amplitude continuously. The intensity can only go up in steps. Okay, you can have 1 photon, 2 photons, 3 photons, or whatever. Okay, so you have these packets of energy. So Planck was the first one who proposed this. Okay, but he himself thought that this is just a mathematical trick. Okay, that light, although it's like a wave, you can think of it as being the energy being carried by these packets of energy, where each packet, depending on the frequency nu, has a certain energy h nu. Okay. But then you can, depend, if the intensity is very bright, you can have multiple packets, okay? Now, Einstein was the one who then latched onto that idea to explain another experimental phenomena around that time that people hadn't been able to explain based on classical physics of the start of the 20th century, and that is the so-called photoelectric effect. What is that effect? The effect is if you take certain solids, such as a metal or certain semiconductors, and I shine light on it with different frequencies and different intensities, so different amplitudes. So you can get weak beam of light or strong beam of light. People found that for very low frequencies, up to a frequency nu naught, nothing would happen. But then once you exceed nu naught, electrons start getting ejected out of this solid. Okay, these are called photoelectrons. And you can then measure the number of these photoelectrons that are coming out, the energy with which they're coming out by simple experiments. You can measure the kinetic energy of these electrons. So the way you would do that, for example, is you can take this simple object, okay, say a metal, and then when these electrons are coming out, okay, you can try to measure the current using an ammeter with a voltage. I'm not drawing it very precisely, but just to give you the idea. So you can have a variable voltage source, and you can measure the electrons that are coming out using some sort of an ammeter, okay? And what you can do is you can have a repelling voltage. If you apply a negative voltage, that'll repel the electrons, okay? So you can figure out what minimum negative voltage I need to apply to cut off the current, the photoelectrons coming off of the solid, and that's how you can measure the kinetic energy. All right. I don't want you to worry about the experimental details that's given in the textbook. What I want to latch on is the broad features of the result. Okay. So what people discovered was the energy with which the kinetic energy with which individual photoelectrons are being ejected did not depend on the intensity of the light. So if it was a low intensity versus large intensity, remember the classical picture tells you that the energy carried by the light or the intensity should be proportional to amplitude square, right? So if you go from a low intensity to a higher intensity, what would classical physics tell you? The classical physics will tell you the kinetic energy with which these electrons would come off should have increased, right? Instead, people found out that the intensity had no effect whatsoever on the energy with which the electrons were coming off. Instead, you're getting more photoelectrons coming out. So the magnitude of the current was going up, but the kinetic energy of the electrons themselves were unchanged. By contrast, at a certain intensity, if you gradually increase the frequency, the energy with which the electrons are coming out was increasing, okay? And this could only be understood if you thought of this light as being carried by these photons of energy. So according to the Planck law, as the frequency goes up, the energy of these individual photons goes up. And therefore, the kinetic energy with which the electrons were coming off, being ejected, is equal to the photon energy minus a constant, which depends on the type of material that I'm shining the light on. And that is known as your work function, okay? Now we'll discuss work function also later on in the context of semiconductors. But just as a preview, you can take this metal and you can draw an energy band diagram of the metal, where this is the energy of the outside. Let me call it the vacuum level, okay? And the electrons in the solid are stuck in this potential well, where this energy is your work function minus Q phi, okay? So the way to understand this in terms of the energy band diagrams is, if I take these electrons in this metal and I absorb a photon up to an energy of Q phi, this work function, they'd be stuck in this potential well. They can't come out, right? It's only when the photon energy exceeds this Q phi, the so-called work function, they can come out of this potential well and be ejected, okay? So clearly then, light seems to have both a wave type property, as shown in this diffraction phenomena, but also a particle type character, the photon type character, which shows up under certain experiments, such as black body or this photoelectric effect and so on and so forth, okay? And then, of course, people started wondering, so if light, which we thought of as waves, has a particle type character, could electrons, which had been discovered by that time, which we think of as these charged particles, maybe also has a wave type character. And indeed, that was the genesis of quantum mechanics. Let's go back to this double slit experiment and revisit this, okay? So like I said, the double slit experiment seems to clearly show that it's a wave type property because of this diffraction phenomena, right? So then what people did was they said, this light source, let's make it lower and lower in intensity. So initially it was a high amplitude light source, and then you make it weaker and weaker, okay, to the point that only a few of these light photons per second or per minute shine through these slits, okay? And then you observe what's happening on the screen. So as you reduce the intensity of the light, what was noticed was initially the intensity of these bands would gradually go down, but then once you went down sufficiently low intensity, people found that the light bands were not just getting dimmer and dimmer, but instead people are seeing specks of light. Maybe you see a speck of light over here, and that's a single photon hitting it. There may be a second speck hitting over there, a third speck hitting over there, fourth speck hitting over there, and so on and so forth. Okay, so suppose it's such a light, low intensity light that I'm only shooting 1 photon per day, say, right? So I'll get a speck of light here, speck of light there, but no specks of light in the dark bands. But then if I keep doing these experiments, the specks of light statistically build up a pattern, which then corresponds to the diffraction phenomena or the interference phenomena. So these individual photon specks of light seem to follow a trajectory which is governed by the waves, the electromagnetic waves. Okay, so it's a very funny concept, right? And if you think about it, it's very, very strange, right? Because if I shoot 1 photon per day, say the first photon today, the next photon the second day, how the heck would the second photon know anything about the trajectory of the first photon, right? I mean, there's no memory that the photons have, but yet mystically, the particle trajectories of the photons are guided by the wave properties, in this case, electromagnetic wave properties. And exactly the same thing was observed with electrons. So when people, instead of shining light, they shine electrons by, creating a filament, heating it up, ejecting electrons, shining it through a screen, and then looking at the diffraction phenomena, see the same thing. Okay, so individual electrons hit the screen as dots, but then if I have a lot of electrons propagating, these dots seem to have a pattern corresponding to a wave property, and this is this de Broglie wave characteristics of the electron. Now, the way the experiment is done in the case of electrons is you don't really shine an electron through a screen like so. You shine it through a crystal, because remember, a crystal has a periodic structure. So when I shine this electron wave through a periodic arrangement of atoms in the crystal, the electrons undergo diffraction phenomena. All right, so the wave particle duality, that's what you're going to build on, okay? So I've told you then that after the light was seen to have both a wave and particle type property, people wondered if electrons and other solids, other particles, not just electrons, any particle would also have a wave type property. So, and the answer is yes, but the question is, of course, how was that shown? How was that proven? So that was shown by the next set of experiments that I'm going to discuss. These were done by doing what is called spectroscopy. Now, what is spectroscopy? In spectroscopy, what you do is you take atoms or whatever I'm interested in, say you can put them in a glass tube as shown over here, say hydrogen or maybe some other gas, or you can heat up a solid, make a vapor out of it, and then you apply a high enough voltage through that tube containing that species, say hydrogen or whatever it is, okay, so that the hydrogen lights up. So that's kind of what you have in your fluorescent light bulbs or arc lamps and things like that. So basically you get light out of it. You pass the light that comes out through some sort of a prism, so that, of course, we know that a prism can take broadband light and you can disperse it into the different colors of light as shown over here, right? Now, you can then look at these particular wavelengths with which the light is being emitted, and you can plot the intensity or the strength at the different wavelengths, just as we saw in the double slit experiment. All right. Now, what was found was, if you look at the spectrum that comes off from a solid, such as a black body that I talked about, okay, so suppose it's a black body, you get a continuous spectrum as shown over here. Okay, so you get emissions at pretty much every wavelength. On the other hand, when people did similar experiments with gases, individual hydrogen molecules, when you excite them, don't have a continuous spectrum, but people observed when you pass it through some sort of a prism type arrangement, you get sharp spectral lines wherever you see these bright lines, but then nothing in between, dark bands in between. And very interesting behavior. So this saw, for example, you saw a sharp set of spectral lines which are kind of clustered together in a very sort of a quasi-periodic fashion. Then you get a large dark region, no emission, whatever. Then you get the next set of spectral lines and so on and so forth. You basically seem to have groups of the spectral lines, okay? And initially it was just observation. People had no idea at all why hydrogen atoms were emitting radiation in a discrete fashion with discrete wavelengths. Mind you, in this case, I'm showing the emission in terms of frequency measured in terms of wavelength, okay? And the reason we can do that is, in the case of electromagnetic radiation, the frequency times wavelength is a constant, the speed of light, right? So although I'm interested in frequency, I'm expressing frequency in terms of the corresponding wavelength, which would be simply the constant speed of light in vacuum divided by the wavelength. So that's why I'm showing frequency, but in units of angstroms or wavelength, all right? Now, to understand this behavior, people introduced energy level, the concept of energy levels in an atom. And so I'm getting ahead of myself a little bit. So people ultimately realized that when you excite hydrogen atoms, you put the electrons in high energy states. And then when they go to lower energy states, that's when they can give off radiation that I'm seeing, but in discrete frequencies corresponding to these photons, h nu. So what I'm doing is, I'm summarizing roughly, maybe 30 years worth of experiments around the 1900. And if you took a physics course, modern physics course, they'd spend almost a semester covering all of this. So obviously I'm leaving out a lot of details. All that I want to do is to get across the basic concepts that we'll be needing for our semiconductor physics description. Now, if you've had a course in modern physics, hopefully this is a refresher and it'll be a lot easier for you, hopefully. All right, so like I said, experimentalists observed these spectral emissions. The first one that was actually observed was this set of lines by this gentleman Balmer. So that was known as the Balmer series, while the other lines were observed later on. Any guesses why? Why was the Balmer series of lines discovered first?
That's the one in the visible portion of the electromagnetic spectrum.
Excellent, very good. Okay, so the visible part of the electromagnetic spectrum, 4,000 angstroms corresponds to blue, 8,000 corresponds to red, okay? Shorter wavelengths is ultraviolet, and this side is infrared, okay? So the visible part, people saw that first. All right, so then a gentleman called Wright Rydberg said, let's look at these frequencies, and you see that you have these discrete frequencies which are seen to be bunched up, and let's see if I can have a mathematical description of these frequencies. And he came up with this formula which fit the data beautifully, okay? So the frequencies of emission were given by a constant, which is known as a Rydberg, times 1 over n1 squared, where n1 is a set of integers, minus n2 squared, where depending on the choice of n1, n2 has to be n1 plus 1, n1 plus 2, and so on and so forth, okay? Now, all that Rydberg did was fit the data to a formula like this. He had no clue whatsoever as to why you have a strange relationship, okay? So to understand that, you come to the next part of the story. And I'm just going to give you the punchline, okay, and then fill in the details. So the story is, of course, if you look at the Bohr model of atoms that I'm sure you've seen in some of the class, you can see that a hydrogen atom will have a nucleus, which is this heavy proton, which is positively charged, and maybe neutrons, depending on the isotope that I'm looking at. And most of the mass is concentrated in this nucleus in the center. And then the electrons then orbit in various shells and subshells around it with gradually increasing energy levels, okay? So what will happen then is, if I excite electrons from lower energies to higher energies, as shown over here, it could ultimately relax from these lower energies to, say, the n equal to 2 shell, okay? From here to the n equal to 2 shell, from here to n equal to 2 shell. So that then explains these spectral lines, okay? Where these are the higher energy states, and n2 happens to be 2 in this particular case, right? So you're going from 3 to 2, 4 to 2, and so on and so forth. All right. So you're going from 3 to 2, 4 to 2, 5 to 2, and so on and so forth. All right. Conversely, if you relax to the n equal to 1 state, then this would be 1, and so on and so forth. Okay. And then once you recognize this picture, clearly you can see that, say, an energy or a photon frequency corresponding to, say, this transition could be broken up as a transition from this to this level plus this to this level, right? So you could add up frequencies of emission and they should add up, right? So this is known as a Rayleigh combinatorial principle and so on and so forth. So the point is, the Ritz combinatorial principle. So the point is, that's how they came up with this mental picture of the energy levels in a hydrogen atom, and then you can extrapolate those to other atoms also. This idea that the mass of the atom was concentrated in the middle, that came from Rutherford. So the initial picture of an atom was, the mass was more or less uniformly distributed, but then Rutherford, in his experiments, he shot alpha particles, which are these helium nuclei, okay, charged helium nuclei at thin foils of gold. And he saw that some of these helium nuclei or alpha particles bounced right back, even though the film of gold that he was dealing with was just a few atoms of gold thick, okay? And he realized that that could not possibly happen if the mass of the gold atom was uniformly spread out. And the analogy that he used was, the fact that I'm shooting helium nuclei and most of them are going through, but yet once in a while, a few of them are bouncing back, is sort of the analog of having a sheet of paper and I'm shooting cannonballs at it. And you'd, of course, expect the cannonballs to just punch right through, right? But surprisingly, maybe 1 in a million cannonballs bounce right back. And that simply could not be explained if the mass of the atom was uniformly distributed, right? I'm not going to go into the details of the scattering process. It could only be explained if the mass of the atom and the charge was highly concentrated. So in that case, then, if this helium nucleus just happened to be in the vicinity of this charge, these positive charges would repel each other. So depending on the exact trajectory of this helium nuclei, a few of them could bounce back. So that was this the genesis of this so-called planetary model, where we think of the nucleus as being like the sun, and then the electrons then orbit in various shells and subshells, just like the planets orbit around the sun. So that's the so-called planetary model. So Rutherford got stuck at that point because he did not figure out exactly how the electrons would be orbiting around the positive nucleus, okay? At that point, there was another problem, conceptual problem that needed to be solved. And that is, it turns out, according to Maxwell's equations, if you have a charged particle, such as electron, orbiting around something, clearly that even if it's orbiting at a constant speed, clearly that electron is undergoing acceleration, right? So this is a centripetal acceleration that we study in physics, right? Because remember, velocity is both speed and direction. And although the speed may be constant, since the direction is changing, it's accelerating. And from Maxwell's equations, it turns out any accelerating charge has to give off radiation. It's known as Bremsstrahlung radiation. And that's obviously a problem then, because what it tells you is no atom should be energetically stable. Because think of this electron, if it's going to accelerate and give off radiation, it should gradually then relax to the nucleus, and atoms should be destroyed. And clearly, atoms are very, very stable. Rutherford is stable, I'm stable, Trump is stable, everybody's stable, right? So at that point, a guy called Bohr, who was a student under Rutherford in Cambridge, he said, clearly electrons seem to have stable orbits. So let me come up with a model for that. And he said that, let's just postulate that electrons can't just have any arbitrary orbit. They can only have certain allowed orbits. I'm putting allowed in quotes because what he's defining as allowed orbits are orbits which satisfy this mathematical relationship. The relationship is the angular momentum P, which is the product of the linear momentum, mass times velocity, times the radial distance. So suppose I'm looking at this electron traveling with a velocity v, and the mass of the electron is m times v times this distance r is known as your angular momentum. That angular momentum, according to Bohr, cannot have any arbitrary value. It can only have values of this Planck constant h divided by 2 pi times integer numbers n. This is sometimes also written compactly as n h bar, but the term h bar is the shorthand for h divided by 2 pi. So those are the only allowed orbits according to Bohr. And the only way electrons can lose or gain energy is when it goes from one Bohr orbit to the other. When it goes from a higher Bohr orbit to a lower Bohr orbit, it gives off a packet of energy, these photons that you observe in the spectroscopy experiments, or conversely, it can absorb specific energy photons and go from a lower state to a higher state. All right. And of course, you should ask, how the heck did Bohr come up with this weird postulate, right, out of thin air? And the answer is because he knew what the final answer was. He knew what the experimental data showed. He knew that the frequencies follow this weird relationship. So he back calculated. Okay. The story is, if I give you a homework problem and suppose the solutions, the final answers are given at the end of the textbook, right? What did you do? You'd work it out. And if you didn't get the right answer, what did you do? You go back and figure things out and figure out what assumptions you need to make to know what the final answer is, right? To get the final answer. So that's what Bohr did. He had to make this postulate to fit the experimental data. And we'll come to the rationale behind that in a few minutes. But so that's how it started, okay? Okay, so the Bohr model that hopefully also you've seen at some point in your AP physics class is very, very straightforward. It's simple algebra. Okay, so I'll just give you the basic steps. So you have the electrons with a negative charge minus q orbiting around this heavy nucleus made up of the single proton in the case of hydrogen, plus a certain number of neutrons depending on the isotope that I'm talking about. Of course, the neutrons have no charge. Unlike charges attract each other with a force which is q squared divided by k r squared, where in MKS units is 4 pi epsilon naught. Epsilon is the dielectric constant of free space. So it's minus q squared over 4 pi epsilon naught r squared. That attractive force is what gives you the centripetal acceleration, right? And the centripetal acceleration is mv squared over r. Okay, that's a centripetal force. Hopefully you remember that from your physics class. Next comes the assumption that Bohr made, or pulled it out of thin air to explain the data, and that is the mass times velocity, which is the linear momentum times radius, which is known as angular momentum. Okay, in many books it's also written as L, but here I'm calling it p theta, is equal to n h bar. So L, angular momentum, is what I'm calling angular momentum, is what I'm calling p theta over here. Okay, that has to be equal to integer numbers n times h over 2 pi, or h bar. All right, the rest is very easy algebra. So you take the square of both sides. All right, and then you write down an expression for the total energy of the system. Okay, now the total energy is the sum total of the kinetic plus the potential energy, of course, right? Kinetic energy is straightforward. It's half mv squared. I have an expression for m squared v squared. So I can divide by m and half, and I get this. All right. How about the potential energy? Well, potential energy for two unlike charges is given by minus q squared over 4 pi epsilon r. Remember that from 325 or your physics 303 L, hopefully. So that's the expression of the potential energy. Now, one thing that I have to mention over here, and that is when you talk about potential energy, it is not an absolute concept, right? Because whenever you ask what the potential energy is, you should also specify with respect to what, right? Because potential energy is a relative term. So in the context over here, you can think of the electrons orbiting around the nucleus as being held by this Coulombic potential well, which has a variation of 1 over r, as shown over here, right? And if you move very, very far enough away, you call that your zero reference, and that's your so-called vacuum level. So, if I was to yank the electron very, very far away from this positive nucleus so that the attractive forces are negligible, that electron will have an energy, potential energy, which I define as a zero of my energy, or the so-called vacuum level. So you pull the electron out of the solid or out of the atom very far away where it's not under the influence of these attractive forces, and you set that as your constant reference as the zero of your potential energy. With respect to that, the energy that the electrons have would be negative because it's an attractive potential. That's why I have this minus sign over here, okay? So it's minus q squared, unlike charges attracting each other, over k, which is 4 pi epsilon naught r, all right? And then, of course, you can plug in the values of Rn, which satisfy these allowed Bohr orbits according to Bohr. Okay, so I'm not going to go to the detailed algebraic steps. I strongly encourage you to, do those. And then finally, you get the total energy, which is, of course, the sum total of this kinetic energy plus the potential energy. And straightforward algebra 101, you end up getting this. So the important point is you get a bunch of constants, which is the mass of the electron m, the q of the electron q, or it's also the charge of the electron q, which is also the charge of a proton to the power 4, 2k n squared, that's a key point, n are these integer values, okay, times h bar squared. Now, everything else is a constant except for the n. If you plug those constants in, that has a value of 13.6 electron volts with a negative sign because it's an attractive potential if I'm in the first energy level n equal to 1, or the ground state of hydrogen. And this energy is known as your Rydberg of energy, after Rydberg, who first made this observation, okay? This is known as the Rydberg constant. It's related to this Rydberg energy, okay? You can also get the expressions for the radii, the various Bohr radii, and the lowest ground state has a Bohr radius of half an angstrom, but then the next one 4 times as large, the third one 9 times as large, and so on and so forth. Okay. Similarly, they have the energy levels which vary as 1 over n squared, and these are what correspond to these energy levels in this picture of an atom, the hydrogen atom. All right. Any questions? Okay, so then the $1 million question is, how does one justify making this weird assumption that electrons can't have any possible angular momentum, mass times velocity times distance to the center, but they only are allowed to have angular momentum in this discrete fashion, discrete numbers n, integer numbers n, times Planck constant divided by 2 pi, right? I mean, that's a very weird assumption. So to explain this, a French physicist, Louis de Broglie, okay? He was actually a prince. He belonged to the French royalty, so it's Prince Louis de Broglie. He was a PhD student, and at the age of 24, the story is he wrote a 7-page PhD thesis proposing his concept of de Broglie waves, okay? And the concept is what I just told you earlier already, and that is, by that time, people had figured out that light seems to have both a wave type character, but also a particle type character, depending on the experiment. He said, in that case, electrons, which up to this point we are thinking of as these tiny charged particles, by analogy, should also have a wave type character, and they are now known as the de Broglie waves. So that was his PhD thesis, and a few years later, he got a Nobel Prize in Physics based on that. He did a lot of other things also, and he also drank a lot of French wine, so very smart guy. So what is his hypothesis? He said that depending on the momentum p of a particle, which is a mass times velocity, there'll be a matter wave associated with that, the de Broglie wave, which is given by the Planck constant divided by this mass times velocity. All right. So if that's the case, then you can just flip terms, and you can say that the momentum of a particle is given by h over the wavelength, or you can divide and multiply by 2 pi. H over 2 pi is what I call h bar, and 2 pi over lambda, the wavelength, is known as a wave vector k, which is what I had introduced at the beginning of the lectures today. Okay, in terms of, so that's the Fourier transform conjugate of the spatial variable, just for future reference. So how does this picture help? Well, this physical de Broglie wavelength picture gives you an elegant justification for the Bohr assumption of allowed Bohr orbits. He said that, if I think of electrons in these orbits having these specific de Broglie wavelengths, the reason you only have certain allowed Bohr orbits are only for those allowed orbits, you can have an integer number of these de Broglie wavelengths forming this nice standing wave patterns. Now, what is a standing wave pattern? Well, as I already told you, if you think of a string that's fixed at the two ends and I pluck it, the lowest mode of vibration is in a half a wavelength, like so, right? Then the next mode of vibration is a full wavelength, and so on and so forth, all right? So these are your nodes, those are your antinodes, and so on and so forth. You get these various standing wave patterns. Well, of course, in the case of electron orbiting around the nucleus, it's more like a circular string. And imagine plucking it. So I can have, say, one standing wave pattern of a de Broglie wave with n wavelengths fitting within the circumference. What is the circumference? The circumference of this orbit is 2 pi r. So if 2 pi r is an integer number times this de Broglie wavelength n pi, flipping terms around, that tells you that h over p, that's your momentum, times r, works out to this. So that's your angular momentum. That then works out to n h over 2 pi. Okay. So basically what this tells you is if the angular momentum is an integer number times h over 2 pi, then you can fit in a discrete number of these de Broglie waves into the circumference. Okay. On the other hand, if I have a scenario where I choose a momentum where you don't fit a discrete number of these wavelengths, you get a mismatch, and that's not an allowed Bohr orbit. Okay. That's not allowed. So that was a very nice, physical picture, which justifies the assumptions that Bohr made. Okay. The next story, part of the story, and that's what we'll stop with today, is by Heisenberg, who, along with Schrodinger, was one of the co-founders of what is called quantum mechanics. So that's what we'll discuss starting next lecture, but I just wanted to introduce a very important concept that was a genesis of quantum mechanics, and that's the so-called famous Heisenberg uncertainty principle. All right. So the question that Heisenberg asked himself was, electrons prior to de Broglie were thought of as particles, which could be highly localized in space. But now Mr. de Broglie is saying, no, it's got a wave associated with that. Okay. And its corresponding wave momentum, which is h divided by its corresponding wavelength, whatever the wavelength is. But if my electron is a wave, like so, I can think of as the intensity of the electron wave, which is equal to amplitude square. So, if this is my wave, I have the electron having a high amplitude or a high intensity of occurring over here. If I square this, it has a high intensity of occurring over here because the intensity of a wave is amplitude square, right? But on the other hand, the intensity or the amplitude at this point of the wave is very, very small. So there's no intensity over here. So the question becomes, I now have some uncertainty, delta x, of the location of that particle, right? Now, at this point, you can use a principle in Fourier transforms, and that is, let's look at the signal in the time domain. Now, if I have, suppose this is a signal in the time domain, f of t, and this is time, okay? Now, if I had a signal which extended from minus to plus infinity in time, and I look at this corresponding Fourier transform, what do I get? I get a very specific frequency, omega naught, say, right, which is the frequency of this sine wave. On the other hand, if I chose something in the time domain, which was a delta function, say, suppose in the time domain, I just had a delta function of time, okay, just an impulse. In the corresponding frequency domain, what will I get? I get all frequency components available to me, right? If you take the Fourier transform of a delta function, you get all frequencies present, right? So you have this relationship between the uncertainty in the time domain and uncertainty in the frequency domain. Similarly, in our case, you have a uncertainty in position and the uncertainty in the momentum space or K space, which according to Heisenberg has this relationship that the minimum uncertainty in position times the minimum uncertainty in momentum or K must be greater than or equal to h over 4 pi or h bar over 2. Once you assume that electrons or other particles have a wave type character, you can't localize the wave precisely. And therefore that then leads to a corresponding uncertainty in position. Okay. So what you need to do then is in order to kind of localize the particle, you have to create wave packets. And the way you do that is, suppose the particle is located somewhere over here, you can define that as a wave packet made up of many frequency components, okay? And you choose them so that you have an envelope which then determines the uncertainty in position. But then to describe this envelope with many frequency components, you can't have just a single frequency. You'll have to have a certain number of frequency components of different amplitudes in the Fourier domain, okay? Now, of course, here it's in the time domain, but in our case, it will be frequency components in the spatial domain, which is given by this wave vector k, okay? So wave vector k is basically proportional to the momentum of the particle, where the proportionality constant is h bar. So in the next class, this is where we start off with, we'll see that in quantum physics, there's two relationships that capture the wave-particle duality of nature. The first was the one given by Planck and Einstein, that's known as the Planck-Einstein relationship, which tells you that the energy is given by the Planck constant h times the frequency. Sometimes that's also described as h over 2 pi or h bar times 2 pi nu. So h over 2 pi, that can be written then as h bar, and 2 pi frequency is frequency in radians per second or omega. So E equals h bar omega is very often the way E equal to h nu is also described. Okay, so that's the first relationship. That's the Planck or Planck-Einstein relationship. The second relationship is the de Broglie relationship that we just talked about. And that is that the momentum is given by h over lambda, as shown over here, or you can divide and multiply by 2 pi, and that can be written as h bar, and 2 pi over lambda is the so-called wave vector k. That's known as the wave vector. Okay, it's basically the reciprocal of the wavelength. So k basically tells you how many wavelengths that I can fit in a certain distance. Okay, shorter the wavelength, I can, in a certain fixed distance, I can pack in more of these waves. Okay, the wave vector k is going to be larger. The wave vector k is basically proportional to the momentum. Now, these two relationships, it turns out, are going to be always true, regardless of whether I'm talking about photons, electromagnetic radiation, or electrons, or matter waves, or if I'm walking around in a Banerjee waves, there'll be a certain wavelength associated with my motion, okay? And they'll all follow these two relationships, okay? And if you think about it, it captures this wave-particle duality concept very nicely, because when I talk about things like frequency, nu, or omega, what kind of picture does it give you? Well, it gives you the concept of some sort of a wave, right? Which is oscillating with a certain frequency. And when you think about energy, I mean, of course, you can have energy of a wave also, but you can think of energy of particles, et cetera, et cetera. How about the de Broglie? When I think of things like momentum, clearly that's a particle type picture, right? Momentum of a particle. On the other hand, when I think of wavelength, or the reciprocal of the wavelength k, that's a wave picture. These two relationships, E equal to h bar omega and P equal to h bar k, is something that's going to be used extensively in our class, and they capture this wave particle duality of, say, electrons or photons or what have you, okay? Now, we'll also then determine relationships between energy and momentum. Now, those will depend on the type of particle that we are talking about. So when we talk about electrons, the energy will depend on momentum as half mv squared, or momentum squared over 2m. That's for electrons or other particles. On the other hand, for photons, the relationship is going to be different. Why? Well, for photons, remember, frequency times wavelength equals to a constant, is a constant c, right? Well, frequency is proportional to energy. If I bring lambda over this side, sorry. If I bring lambda over to this side, 1 over lambda is proportional to k. Okay, so you'll see here that energy will be proportional to momentum for photons. Here, energy is proportional to momentum squared for electrons, but for photons, there's a linear dependency. Okay, so these types of relationships between quantities in equation 1 and 2 are dependent on the type of particle that we're looking at, but these types of relationships are universal. Okay, so that's where we'll start off next week. Thank you.
Thank you.
Thank you.